PowerPoint slide?
Yes.
Yep.
Okay, that's good. So basically in these like approximately, I guess, 20 minutes talk, so I'm going to talk about what I have done in 3 years for at Macquarie University, leading to PhD degree. So basically, this is the title of my PhD, and this is based on the following works. And yeah, if anyone wants to see the relevant paper, you are welcome to do that. Let me first give the context of this, so you guys can hear me well, right?
Yep.
Okay,
Okay.
right. That's good. So let me first give the context of context. So basically, on observation, talking from the observational viewpoint, there are hundreds of massive compact objects which mimic the properties of black holes within the current experimental bounds. And we try to model those objects as physical black holes. And for us, physical black holes is the object which contains horizon, and those objects to be relevant for practical purpose should form in finite time of a distant observer. And if we see the chart of on the possibility of all the astrophysical black holes, what astrophysical black holes could be, surely the object of compactness, which are lesser than one half of the object, which are like not more compact than one half of the horizon radius, are already excluded by Event Horizon Telescope. So based on current observational bounds, at least the object should be more compact than the light rings. And so here are like a lot of like horizonless objects, hundreds of horizonless objects, and some horizon objects with horizon, which are the possible candidates of astrophysical black holes. And based on that, they could be classified as exotic compact objects, ultra compact objects, and physical black holes. Basically, physical black hole include objects like mathematical black hole and regular black hole, and examples of mathematical black holes, some of which we know are popular black hole solutions of general relativity, like Schwarzschild and core black hole solutions. And some of the examples of ultra compact objects are boson stars and Grava stars. So basically, we try to model astrophysical black holes as physical black holes, which could be mathematical black holes and regular black holes, or any other objects containing horizon. And it turns out that when we define physical black hole that vaguely, there are like tens or more 20s definitions of horizon, and we should be more precise than saying that black holes are object containing horizon. Uh, So basically, one of the most popular notion of horizon is event horizon, and event horizon is defined as the uh, boundary like outside which the inside event cannot affect. So observer outside the boundary of the event horizon cannot be affected by the observer inside. By this definition, event horizon is a teleological entity. Uh, we can just see this based on the fact that event horizon is commonly a surface from which nothing can escape. And if like there is some dynamical surface from which like nothing can escape now, and however, like if something escapes in the future, then by definition that is not an event horizon. So to locate event horizon for all practical purposes, we need to know the evolution of some compact object or black hole to the entire history of the universe. In that sense, event horizon is teleological entity, and we cannot physically observe that even in principle. And thus, numerical studies focuses on other characteristic of black hole. And by definition, the core property of black hole is that it should not allow light to escape at present or now. So the notion of dragging back of light. So if we can express the notion of dragging back of light mathematically, then that will capture our common understanding or intuition of black hole, and that can be expressed mathematically by using the idea of closed trapped surface, which was initially introduced by Roger Penrose in his famous or Nobel Prize winning paper. So we define black hole, physical black hole, precisely as a trapped region from which can drag back light, or from which light cannot escape at present or now. And the outer boundary of that of the physical black hole is apparent horizon. So to make that definition, to make sense of that definition, or to extract observational feature or properties from the definition, we start with some general spherically symmetric metric in Schwarzschild coordinates. Basically, this is the most general form of metric, spherically symmetric metric. And here, like, if we note at this metric, look clearly at this metric has two independent parameters. And if we can somehow specify two independent parameters, then the problem is solved. We know everything about the space-time that is described by this metric. And we are writing this metric in some coordinate form, which is very familiar to us from our studies in curvilinear coordinate. If we see, so can you see my cursor?
Sort of when you move it, yeah.
Oh, okay, right here. So if we see this angular part, so this angular part has the coordinate, and this contains the radial coordinate, and this radial coordinate is the areal radius, it specifies the area of the cone, which this angular part omega describes. And if we write the metric in this areal coordinate, we have an invariant notion of mass m, which we also called Misner-Sharp mass. So we have a lot of bonus here writing the metric in this coordinate. And for this metric, so the apparent horizon, which is the outer boundary of trapped surface, which can drag back the light, is r equals to twice m surface. And our objective is to study the nature of space-times near this surface, near the apparent horizon. So in general relativity, there are various. So basically, if we see this metric, so this metric is written in some particular coordinate form, and if we do coordinate transformations, the structure of the metric will be completely different. However, like, there are various quantities in general relativity which doesn't change even if we change coordinate systems, and among them we focus on curvature invariants. We focus on curvature invariance to study the features, or to make the properties of physical black holes mathematical. First thing, like, we starts from this Einstein tensor, which is defined in following way. Here R is Ricci tensor, R mu nu is Ricci tensor, and R is Ricci scalar, which is constructed from Ricci tensor, which is the contraction of Ricci tensor. And we impose the regularity condition. That means that if we have some notion of invariant curvatures constructed from curvature tensor, we assume that at the boundary which is even apparent horizon, we assume the regularity or the finiteness of those invariants, for curvature invariants. For our purpose, like there are theorems which says that in like general normal space-time, spherically symmetric space-times, there are like 16 curvature invariants that can be constructed, or like 16 curvature invariants are required to specify space-time completely. However, in this situation, for our case, 3 of the curvature invariants are sufficient, and third curvature invariant is just to check the consistency of the resulting solution. And just to give the example of how to construct curvature invariant from Einstein tensor, which is defined in this way. So if we contract Einstein tensor with metric, so we have one of the curvature invariant, and if we square that, so we have another curvature invariant, and we can do multiple squaring, and we can construct higher order tensor and contract with metric to construct here other curvature invariant. However, for us, like these two are sufficient to extract the properties of black hole, physical black holes, and the third one, we can use third one to study for the consistency check. So our basic equation is contracted Bianchi identities. So we assume that this semi-classical form of contracted Bianchi identities is satisfied, which is satisfied usually in any metric theories of gravity, independent of the Einstein's theory. So this is the property of metric, and if we substitute, so for G mu nu, if we substitute this equation, and if we calculate Ricci tensor and Ricci scalar for this general metric, then we have only 2 non-trivial equations in the case of spherical symmetry. So that's easy. And to further simplify the equation, as we are only focusing the properties near apparent horizon, we assume that.
Pravin, just ask you a question. So are those, is that bracket notation? Are those quantum states?
Oh yeah, this is just semi-classical quantum semi-classical averaged value of Einstein tensor. So yeah, this is bracket notation, quantum states.
So they are quantum states. Is that a quantum state? Then G mu nu needs to be an operator.
Sure, yeah, it's operator.
But so far you haven't defined it as an operator.
Just as we are doing only as we are restricting ourselves to semi-classical physics, so we are assuming that operator has some eigenvalue or some classical associated classical variable. And for us, like we are not restricting ourselves to particular quantum states or like that. So we are not specifying any quantum states. So yeah, I don't think that will be. However, so this, if written precisely, here should be operator notation here. So
keep going. I understand it maybe later.
Sorry.
Can I ask a very quick question?
Sure.
So the way that you define the Einstein tensor, so why does it have a minus sign out the front? So I thought the Einstein tensor is usually the Ricci minus a half GR. So
you mean? So
yeah, exactly. So I thought it was usually without the minus sign, but.
Oh yeah, maybe probably Einstein tensor is bad notation here, but anyway, yeah.
Okay, fair enough. I mean, so it's a choice.
Yeah, just to cancel out extra minus sign, so I have defined in that way here. But
okay. And yeah, so I also wanted to ask a question about this bracket, but maybe so even more kind of stupid question. So what does the subscript phys mean on just one of the?
So this is just some physical quantity, which is what we get after renormalization. So the expectation value of renormalized energy momentum tensor here, Einstein tensor is, if we just take the divergence covariant derivative of expectation value of the renormalized Einstein tensor, then that's basically semi-classical form of Bianchi identity, and that will be 0. So we are assuming that somehow that quantity is could be renormalized, and that is renormalized.
Okay.
So we are taking the near horizon solution of this form of this perturbative expansion, and if we substitute that back, so we have said that there are only two non-trivial equations. So these basically, so this is 4 equations. There are two angular parts which are which trivially satisfy our initial assumption here, and hence there are only two non-trivial equations. And if we substitute this answers to the non-trivial equation, then we have, in the leading order solution, we have only one equation. And basically, since in the leading order we have only one equation, we don't have enough constraint to determine the exact value of coefficients from that answers. So beta. However, what we know is from our assumption, apparent horizon exists, or this is black hole solution. So at apparent horizon, that answer should vanish. So by definition, apparent horizon is r equals twice m. So this should vanish. So we know that this beta should be greater than 0 as r goes to twice m. In the static limit, so we can immediately solve this equation, so no problem at all. And in that case, so we have a familiar black hole solution, and from this what we can conclude is static black hole solution in any metric theory of gravity would preserve Schwarzschild form. And if we look at static black hole solutions in other theories of gravity other than Einstein theory, then they all have Schwarzschild form. So going to dynamical solution, so just substituting that answer into solving this equation in the leading order just gives e to the power h as this thing. And here is two solutions based on the fact that there is one is growing black hole solutions based on the dynamics of apparent horizon, and another is evaporating black hole solutions. Evaporating solution, one is growing and another is evaporating solution. And if we substitute the solution back into metric, so this e to the power h is, if we look at the metric, so I think quite far. So this e to the power h is one of the free parameters. So if we substitute that back into the metric, we have this quite unusual looking form of the metric, where here is divergence in t square term, g tt term, and divergence in g rr term also. And however, we know that this is some familiar form of the metric. We know Vaidya metric, which is a most common non-trivial dynamical black hole solutions, and this Vaidya metric is very commonly used to model evaporating black hole solutions. And one of this Vaidya metric is, if we do some coordinate transformations, is of that form. And this Vaidya metric in different coordinate system, completely different, which we call Eddington-Finkelstein coordinate system, has this form, which does not look like this diverging form at all. And one of our basic result is our calculation the black hole solution which we have obtained does not rely particularly on Einstein's theory of gravity. So this is valid in all metric theories of gravity. And yeah, just to summarize the results, so I have just presented in this way, so that like it would be convenient to present in this 10-15 minutes. However, yeah, just to summarize what we have, the results we have obtained, before going to specific examples on physical black hole. So we have obtained that null energy condition is violated in the vicinity of apparent horizon. So what do we mean by null energy conditions? Basically, in classical physics, energy is positive. However, in Einstein's theory, so everything is formulated in terms of tensor, and instead of like scalar energy, we have 16 components energy momentum tensor, and we believe that there should be something which we can construct and which based on classical analogy should be positive. And based on that analogy, we have various inequalities. For the positivity of energy, and one of the weakest form of inequality for the describing the positivity of energy in general relativity is null energy condition. And if null energy condition is violated, all of the energy conditions are violated. So this null energy condition is violated in the vicinity of apparent horizon. So by our assumption, we have constructed physical black hole solutions in such a way that there is no strong curvature singularities. However, the solution is still weakly singular at the apparent horizon. So we have basically calculated the energy density and tidal force of the observer, which is trying to escape the apparent horizon, which is going outward towards the apparent horizon. And from that calculations, so we have found that those quantities, energy densities perceived by the observer and tidal forces perceived by them are infinite at the apparent horizon. So apparent horizon, although we have tried to make them we have tried to remove strong curvature singularities, still has weak curvature singularities. In this completely generic way of constructing physical black hole solution, we have not obtained growing black hole solutions. So there is only evaporating black hole solutions. And we have also shown that in the limit of small evaporation, so if in the macroscopic regime, if the black hole is very, very large, then the Planck scale, size of the black hole is large than Planck scale, then Vaidya spacetime, which I have shown before, serves as a very good near horizon approximation of a black hole. And recently there were papers which were quite popular in the news, and those papers showed the result or argued that black holes in cosmological spacetimes are or should be coupled with cosmological constant. And that was quite a surprise to the scientific community. However, for physical black hole defined in this way, those physical black holes can be consistently embedded into cosmological background without requiring any cosmological couplings. And the presence of trapped region does not impose any additional conditions than the conditions which I have talked before. Even if we talk about the physical black holes embedded in de Sitter or any cosmological backgrounds, just the location of apparent horizon is slightly modified by this Hubble constant. So these are the basic results from our self-consistent semi-classical study of physical black holes, which is a compact object containing trapped region. And to give a particular example of linear Vaidya metric and how it is compatible, and how these solutions which we use to model evaporating black hole is compatible with physical black hole solutions. So let's talk about linear Vaidya metric. So basically we know that linear Vaidya metric is conformal to some static metric, and for this metric we can derive Hawking effect from first principle and generalize the laws of black hole thermodynamics. If we apply these coordinate transformations, so these coordinate transformations to the linear Vaidya metric, to the metric written in this coordinate, which is shown here. If we change the coordinates, so here basically the metric is written in V and R coordinate. And if we change the coordinate V and R into capital T and capital R, then we can basically write that metric, which is dynamical metric, as some time-dependent part times the completely static form. And if we have metric in static form, if there is static metric, then we have the notion of event horizon. The problem which we have talked about event horizon before, so that doesn't exist in static or stationary spacetimes. So this metric has event horizon at this location. Similarly, there is another notion in static spacetime, another vector notion of vector, so which is Killing vector, and Killing vector are infinitesimal generators of isometries. For example, in static spacetime doesn't depend on time coordinate, and if we do infinitesimal time translation, then the metric doesn't change at all. So Killing vectors are just infinitesimal generators of isometries. And if there is the notion of Killing vector in some static spacetime or stationary spacetime, then we have the notion of conformal Killing vector in the spacetimes, which are conformal transformations of that static or stationary spacetime. And in the specific example of previous metric, Vaidya metric, we have the conformal Killing vectors. Since we have shown two different coordinates, so we have this Killing vector of this form in two different coordinates. And if we see in second coordinate, we have, so this is just infinitesimal time translation vector. So, and the existence of conformal Killing vector allows the definition of another notion of horizon, which is known as conformal Killing horizon. And this conformal Killing horizon is the Killing horizon in the static counterpart or stationary counterpart, stationary spacetime, corresponding stationary spacetime. And usually this notion of Killing horizon coincides with the notion of event horizon. And furthermore, like if we do further coordinate transformations from uppercase T and uppercase R into Schwarzschild coordinate, so these coordinate transformations, the exact form is not important. However, I just wanted to show that we have the form of metric. And if we see GTT metric, TT component of the metric and RR component of metric, we have the divergent form here in different coordinate system. We started with perfectly fine metric, which was not divergent at all. And we have now like writing in Schwarzschild coordinate. So we have the divergent form here. And we can, if we compare this with the solution we have previously obtained, generic solution we have previously obtained. So this also has divergence in GTT time component and radial component of the matrix. So basically that example, which is the popular model of physical black hole, popular model of evaporating black hole solution, is our physical black hole solutions. And this is also, as we have shown, exactly solvable model, because we have just obtained this solution from direct coordinate transformations using conformal transformations, assuming that the evaporation is linear. And comparing this metric with the general spherically symmetric metric, which I have shown in the beginning, so we can write the integration factor. And from this, like, we can study evaporation law in different coordinate system. Just remember that we have started with linear evaporation law in Eddington-Finkelstein coordinate. However, in Schwarzschild coordinate, we don't have linear evaporation law, and we have seen in the literature that people use the same Page's evaporation law in different coordinate system, like both advanced and retarded Eddington-Finkelstein coordinate and Schwarzschild coordinates. So we have like explicitly shown here that the evaporation law should not be equivalent in all coordinate system. They differ slightly. However, if the evaporation is significantly small, then we can basically see that this can also be reduced to linear form. So, so this was just the example that linear Vaidya metric, which is the popular model of evaporating black hole, is of the physical black hole form, and the solution which we have obtained, which looks like strange in Schwarzschild form, is actually compatible, or is actually the real black hole solution. And so based on that Vaidya black hole solution, we have also studied the particle production on that dynamical background using the Bogolukov transformations method. And since linear Vaidya metric is the conformal transformations of some static metric allowed this study. So this study of particle production of this sort of metric by the exact calculation of Bogolukov transformations was not done before. And we have also generalized the laws of black hole thermodynamics to these special class of spacetimes, dynamical spacetimes, which are conformal to stationary spacetimes by using the fact that Vaidya metric, or by using the fact that in these conformally transformed dynamical spacetimes, there exist conformal Killing vectors, and we have followed an analogous approach to the stationary spacetimes. So basically, I wanted to mention these things, and thank you for listening.
Thank you. Let's go back to your last slide.
This one?
Yeah, this one. This is stuff you've done or stuff you plan to do? Oh,
no, this stuff we have done. However, I have just written the result here.
Well, so the first line, you said you studied the particle production in linear radius space. I'm using the Bogolukov transformation. Did you show that in this presentation? Because I didn't see that.
Oh, no, I have not. So I have not shown that here. However, it is contained in, if I go to first slide, so yeah, it's on this paper number 6.
Oh, okay, sure.
So yeah, I have just mentioned the result.
Oh, okay, I understand. Yeah, so let's go back to my previous question. So you sandwiched the Bianchi identity in between two quantum vacuum states, but you never actually used it again. So why did you ever write this down? I don't understand this.
Just to say that, yeah. So since we don't have to specify any quantum states or like that, so if we assume that this Bianchi identities could be renormalized in semi-classical, then our study is a semi-classical study, right? In the semi-classical, yeah. So, and the solution we are deriving has the possibility to model black hole evaporation. So since we have a solution in the dynamic limit, and in some approximation, this solution models the Hawking effect also. So yeah, this is valid in semi-classical limits. So, however, yeah, we are not specifying any specific form of energy momentum tensor or its excitation states.
Questions?
Yeah, you have to forgive me because I'm pretty new to this kind of field. So in no particular order, when you were talking about the time-like killing vectors for your metric, that's one generator of isometries in that metric, but also because the metric is spherically symmetrical, then there should be another killing vector which generates rotations
Rotational
of the
symmetry.
static
Yeah,
solution.
yeah,
So
right.
where does that fit into? So here's my question. You use the time-like killing vectors here to map a dynamical metric into a static metric, right? Is there an equivalent for the rotational killing vector? Is there an equivalent physical?
Basically, in spherical symmetry, this time-like killing vector is sufficient to locate killing horizon, and thereby, since killing horizon coincides with event horizon, so this time-like killing vector is sufficient to locate event horizon in spherical symmetric case. However, if we have axial symmetric, the simplest example is core metric, which is stationary time. So that has both time-like killing vector and rotational killing vector. And some specific linear combinations of both the killing vector is also a killing vector. And we require that specific combinations of both the killing vectors to determine the event horizon, the killing horizon, and thus the event horizon of core metric. So yeah, this like the another killing vector is not relevant here since the metric is spherically symmetric. And we know like all of the like physically relevant quantities of this spherically symmetric metric will be independent of theta and phi coordinates in the axially symmetric metric, so they are relevant. And yeah,
I think I'm trying to remember. So I think there's something called the Nordstrom metric or Nordstrom representation.
oh yeah, so Reisner-Nordstrom black hole, which is charged black hole solution.
Sorry, no, I'm thinking of this one. The one where, so it's just to address Kieran's question about the rotation. There's one where you can, I can't remember the name, Nordstrom something, which yeah, you can map like a rotation to a stationary, like the way that he maps it.
Okay, so
there is that exist.
Okay, fair.
Yeah, so I keep going. I'll look it up.
And so this is a bit more of a broader question, but as I understand the Schwarzschild solution, the singularity at the event horizon is a kind of an artifact of the coordinate system.
Oh yeah, right.
So you have a true singularity at the center of the black hole.
Exactly, yeah, center, yeah, right.
Yeah, but the event horizon is kind of it's an artifact of the
coordinates. Yeah,
and
right.
You can gauge it away, right? You can gauge transform.
So
so the part that I'm missing here is it that you found a new coordinate system at the event horizon which sort of partially removes singularities? So you show that there's still singularities in the time-like and the R part of the metric, so the TT and the RR.
So let me go to the form of the metric. So although like this metric looks singular, so this metric does not necessarily have singularity, and we know that like this is one of the way to represent general spherically symmetric metrics. No matter like how we represent, so this metric should have two independent functions, and that's general spherically symmetric metric in general spherically symmetric metric. Yeah. So what we are doing here is if we write this metric under some special assumption or circumstance takes the form of Schwarzschild metric. So we call this general form as a Schwarzschild coordinate. This general coordinate are Schwarzschild coordinate. And although like Schwarzschild metric has singularity in the metric in coordinate system, so that's not singularity. So however, like in dynamical black hole solutions, we are not restricting ourselves to only Schwarzschild. So there is no guarantee that there is no like singularity at the horizon. So we are like using the weakness of this coordinate system, apparent weakness of this coordinate system, the apparent divergence of this coordinate system. We are assuming that there is no divergence. However, like this coordinate look divergent, and we are like using this weakness of this coordinate system to extract some additional equation and to extract some physically relevant, meaningful things. So we are just assuming that there is no curvature singularity. That's assumption, but we know that like that is the case for Schwarzschild solution. And if we assume that, like no one is going to argue that, so we are making that assumption, and based on that assumption, so we are extracting physical quantities, and apparently, like we later find that, like if based on that assumption, one of the specific solution is Schwarzschild solution, so it's completely compatible with Schwarzschild. So yeah, that's.
Okay, so just so you have the general spherically symmetric static metric where you have this H and F, which is completely general, right? That's
right,
where you start from. And then this is the part where I'm missing, like what's the assumption on the functions F and H, which then eventually you get to a Schwarzschild metric after you do all your coordinate transformations and things.
So no, like there is no like specific assumption on function F and H. So of course, like so we can write F in this way. It's just like making convenient. So writing one parameter into another form, and we have like some coordinate. If we have like this R as areal radius, then this MTR is invariant quantity. Still like completely general, free. So free parameter. We are not making any assumptions on these free parameters. We are just assuming that these quantities, although like there is like divergent terms in the denominator, approaching to zero terms in the denominator, we are assuming that these quantities should be finite. And if that is the case, then the numerator also should go to zero, right? And we have like different equations. So we are not assuming anything on parameters. We are just assuming that these curvature invariants are finite, and from that we have independent equations to solve the system.
Okay, yeah, I understand. Yeah, and so this is a really naive question, but why you choose those invariants and not, I don't know, something more direct, like with like contractions of the Riemann tensor, or so why you use the Einstein tensor instead of Riemann?
Oh yeah, so Einstein tensor. So this is just second order contraction. So we like increase the complexity one by one. So we have like second order contraction. So these both are second order contraction. And if we go to the third curvature invariant, we need to go to that fourth order contraction. And if we solve, so this is spherically symmetric system. And if we solve general axially symmetric system, we need to go to fourth order. We need to take fourth order invariants also to solve the system. We have not managed to do that generically for fourth order system. We have verified that these physical black hole solutions is compatible based on a specific example. And the plan like initially was to solve axial symmetry also generically. So we need to go that. So that is like another level of complexity, and we need to go that level by level. However, so for a spherically symmetric case, fortunately, like this was sufficient.
Is it necessary but not sufficient, or sufficient but not necessary? I mean, in principle, shouldn't you show that
Oh no, like what we
tensors
have.
that-
Oh, we have like calculated all 16 curvature invariants after 16 curvature invariants after making them finite after forcing them to be finite, and all of the rest are finite.
But you know, I could construct a new invariant, so like I don't know, capital G contracted with a Ricci tensor or some I could dream up something.
Oh yeah,
And,
surely, but
yeah.
that is not necessary here because two of these are sufficient to get the required number of equations to constrain the spherical symmetric matrix. So yeah, that's not sufficient. You can imagine any form of like invariant quantities, like you can contract this Einstein tensor with Ricci tensor. However, like, so there are like in normal, like simplest situation, there are 16 of those invariant quantities, and no matter like how many invariant quantities you imagine, you can express that as a linear combination of 16 of those quantities. And for us, like, fortunately, these two were sufficient. And we also took third to check the consistency of our solution. But these two are completely sufficient to get the solution.
So your claim is that constraining all the 16 invariants here is sufficient and is necessary.
So,
or it's just sufficient.
So these two invariants is sufficient, and 16 is not. I'm saying that 16 is not necessary here in this case for this spherical asymmetric metric. Only two is sufficient here.
Okay, cool. Yeah. Okay, now I need to read the papers.
I mean, short on time, so unless there's any other burning questions, I'll end the meeting there. Okay, cool. So I'll stop the recording.
Cancel sharing, so I can stop sharing, right?
Yeah, you can stop sharing. Stop the recording. Okay, so I just looked at my schedule.